All right, here we got a basic two box and pulley situation. We've got a 45 kilogram box hanging off the end of like a table or something like that with a pulley attached to an 83 kilogram box. Now let's start off nice and simple to begin with. Let's say for our setup here, let's just say that there's no friction. I'm not going to worry about friction to start out with. So we've got no friction to go with. And what we're going to do is we are going to find out what is the acceleration of the boxes. All right, so let's just piece a couple things together here. Now, first things, let's see, I usually think, what's pulling it, what's trying to slow it down, that type of thing. So if I think about what's pulling, only the box hanging off the edge is actually pulling. So if we cut the rope, the 45 kilogram box would fall, the 83 kilogram box would do nothing. So only really the 45 kilogram box is actually pulling, and of course it is pulling with gravity. So if I would do the force of gravity for that box, if I find the mg for that box, so 45 times 9.81, if I calculate that, I'm looking around 440 newtons. So that is how much is pulling. This is my applied force for the situation. There's nothing else pulling really. It's just that one box. So that is my applied force. No friction, so nothing slowing it down. So I can actually use that to find the acceleration. If I was going to look for acceleration, acceleration of course is net force divided by mass. Now in this case, look how much is pulling. Well, I've got 440 newtons is trying to pull it. There's no friction, nothing else slowing it down. So that's it. That would also be my net force. So this would also be my net force in this situation because nothing else is pulling or trying to slow it down. Now I'm going to divide it by the mass. Now I'm going to use the total mass. The two boxes are tied together, so they sort of like become one thing. And both boxes are moving. So you got to look at the total mass that's actually moving. So if I put those two together, that is 128 kilograms altogether. So I'll do the 440 divided by 128. And we are looking at an acceleration of around 3.4 meters per second squared. And of course, it would be going something like this. All right, so let's change the situation a little bit. Let's modify it a little bit and see what else we can do. Now, suppose this thing is in dynamic equilibrium. So now, of course, these words mean sort of important stuff here. Now, first of all, equilibrium, of course, that equilibrium thing, that tells me that the net force has got to be equal to 0 and there is no acceleration. So everything's canceling out, hence the equal thing. All the forces are equal, net force is 0, no acceleration. But the dynamic tells me that it's actually moving. So, I mean, there's static equilibrium where things are just at rest sitting there, but there's also dynamic equilibrium where things are moving, but they're not accelerating. So this thing is still moving, but it's not accelerating, so the net force has got to be equal to 0, hence dynamic equilibrium. Now, if that's true, if I look at what's going on, I've got 440 newtons is trying to move this system. So I've got 440 newtons. This is my applied force. That's how much is trying to move it. Well, if the net force is 0 and it's not accelerating, if I've got 440 trying to move it, I must also have 440 newtons, which is trying to slow it down. Okay, so that way things cancel out. 440 is trying to move it, but the net force is 0. I must have 440 trying to slow it down, which tells me this has got to be how much friction I have. So now if we look where the friction would be, of course, you could have friction in the pulley, but we're just going to work with the little box here. The friction is right here between the 83 kilogram box and the table. So let's see if we can find out what is the coefficient of friction between the box and the table. Now, if I'm looking for the coefficient of friction, of course, coefficient of friction is FF over Fn. Well, I already know how much friction I have. I must have 440 newtons of friction because that's how much the system is pulling with. That's what the little red box is pulling with. That must be how much friction is pulling with or trying to cancel out. Okay, so I know my friction has got to be that 440. So that is taken care of. I know it's 440. But my Fn, where's my Fn? Well, my Fn is between the box and the table, and of course there's force between them. There's normal force between them because gravity is pulling down on that box. So that would just be the weight of the gray box, not the pink one. The pink one has nothing to do with the friction. It's all about that gray one. So I need to use the 83 kilograms and the 9.81 to get the weight of the box. So if I do I'll put over here. If I do the mg for that box, we're looking around a weight of 814 newtons. So if I do the 440 divided by the 814, I'll divide the two out, and I get a coefficient of friction of about 0.54. Again, unitless because there's newtons, and the newtons actually end up canceling out. So then the coefficient of friction would just be 0.54 between the 83 kilogram box and the table.